Statistical thermodynamics. So this statistical thermodynamics was developed by Boltzmann in Germany, and concurrently it was developed by Gibbs in USA. The theory of statistical thermodynamics was modified to some extent by S. N. Bose in the year 1894 to 1974 and Einstein from Germany in the year 1879 to 1955 and Enrico Fermi from Italy in the year 1901 to 1954 and Paul A. M. Dirac in the year 1902 to 1984. The statistical thermodynamics is applicable for molecules, photons, elastic waves of solids, abstract entities such as wave function, electrons, bosons, mesons. This statistical thermodynamics is evaluated on the basis of entropy. So, as we know, entropy is the randomness of atoms and molecules in the system. All models are aimed and designed in finding out the entropy. The study of relationship of thermodynamics is classical thermodynamics, and the task of statistical thermodynamics is establishing the relationship between non-thermodynamics and thermodynamic property. There are two types of thermodynamics. One is thermodynamic, which is otherwise called as macroscopic thermodynamics, and non-thermodynamics, which is otherwise called as microscopic or microscopic thermodynamics. Here, the non-thermodynamic property describes with the ultimate characteristics of the particle, and the thermodynamic properties describes about mass, shape, size, position in motion. There are different models how the statistical thermodynamics is defined. The main models are of three types. One is Bose-Einstein model, second one is Fermi-Dirac model, third one is Maxwell-Boltzmann model. Now we will see the difference between all three models. These are the three differences between all three models, and the sum of the properties have been discussed here. In the Bose-Einstein model, we have identical properties and the particle size is indistinguishable, the wave function is symmetrical, and the state of system is determined if number of particles in a given quantum state is known. No restriction on the occupancy of the particles in a given system. Application to alpha particles, light quantum, deuterium, all atoms, molecules composed of even number of elementary particles like carbon, nitrogen, oxygen, carbon dioxide, etc. And the values are eigenfunctions are symmetric in nature and they are called as bosons. Under the characteristic nature of the Fermi-Dirac model, we have the system of identical particles. The particles are indistinguishable. The particles satisfy the Pauli's exclusion law. So, the Pauli's exclusion principle states that there is never more than one particle in a given quantum state. Applicable to all elementary particles, electrons, protons, neutrons and positrons. The spin is equal to half or odd integral multiple of half. The values are antisymmetric eigenfunctions and they are called as fermions. Here in the Maxwell-Boltzmann model, the particles are distinguishable and non-distinguishable particles which take part in the entropy relationship. Now we will discuss about Boltzmann equation. Boltzmann equation is defined as the probability equation relating to the entropy with the alphabet S of an ideal gas to quantity W, which is number of microstates corresponding to given macrostate, where S is equal to K log W, where K is Boltzmann constant, equal to 1.38062 into 10 power minus 23 joules per Kelvin, and W is number of microstates and macrostate. This follows the relationship of atomic arrangement and relationship between entropy. The Fermi-Dirac statistics describes the distribution of system comprising many identical particles that obey Pauli's exclusion principle. Pauli's exclusion principle was developed by an Austrian physicist, Wolfgang Pauli, in the year 1925. Quantum mechanical principle is that the number of two identical fermions may occupy the same quantum state simultaneously. When we look at the Fermi-Dirac distribution for a system, there are identical fermions with the average number of fermions in a single particle, which states with the given Fermi-Dirac distribution, and the equation is defined as Fe is equal to 1 by 1 plus e to the power e minus ek divided by RT, and Ef is equal to Fermi energy or Fermi level. K is Boltzmann constant, which is equal to 1.38 into 10 power 23 joule per Kelvin, and T is equal to absolute temperature in K. We will look at another property of statistical we will look at another property which is called as partition function, and this is a statistical property in the thermal equilibrium. The partition function of temperature and other parameters are volume. The thermodynamic variables such as total energy, free energy, entropy, pressure is expressed in partition function, and there are two types of partition function. They are canonical partition function and grand canonical partition function. Canonical partition function applies to canonical ensemble in which the system is allowed to exchange heat with the environment at fixed temperature, volume and number of particles, and the grand canonical partition function is the ensemble of the system which can exchange both heat and particles with the environment at fixed temperature, volume and chemical potential. Canonical ensemble is the thermodynamically large system which is in constant thermal contact with the environment with temperature T. Both volume of system and number of constituent particles are fixed. The canonical equation is partition function Z is equal to sigma e power minus beta Eb divided by S, and inverse temperature is beta is equal to 1 by kBT.